Today I'm going to be talking about control charts, which are one of the 7 basic quality tools. Control charts are a great way to visualize data, and you see them very often in industry. Alright, so just for your reference, there are 7 basic quality tools that industrial engineers, quality engineers, anyone seeking to do process improvement really likes to use. They're very simple tools that really help you analyze data in a simple but effective way. Hopefully I'll do videos on all of these eventually. You have cause and effect diagrams, check sheets, control charts, histograms, Pareto charts, scatter diagrams, and stratification. Those are the 7 basic quality tools. In this video, I'll be going over control charts. It's worth noting that these tools are also called the old 7, the first 7, and the basic 7. At least that's what ASQ says. And ASQ is the American Society for Quality. ASQ is the main quality certification body in America. So if you've ever heard of people having green belts or black belts and they're through ASQ, it's a very official certification to have. Alright, so what do control charts even do? Well, control charts study how a process changes over time. Control charts have control limits to help determine if the process is stable or not. So you have an in-control process, which is good, and an out-of-control process, which is very bad. You will often see control charts used in pairs. I'm going to show you the most basic kind, but you'll often see other kinds focusing on range changes. I won't talk about that in this video, we'll keep it simple. Control charts are great visual tools for noticing trends. And there are general rules that can tell you the trends. Alright, let's have an overview of how to make a control chart. We'll go into more detail in a second. So first off, record your times that you're going to be collecting data. It's good to convert your times to simpler numbers, so don't have 10:30 a.m., 10:35 a.m., 10:40 a.m. Just keep your times simple, time 1, time 2, time 3, etc. Then make sure you record the values at each time. For control charts, you can only measure one item. So choose your critical features on your part, or just have multiple control charts for each dimension. Then you'll need to plot the average. You'll also have to determine your standard deviation. Then you'll need to plot a line that's 3 standard deviations above the average. And you'll have to plot a line that's 3 standard deviations below the average. So here is our numerical data larger. I like this slide because it really illustrates why control charts are so useful. Looking at this data, do you notice any patterns? Not immediately. If you're good at statistics, you could look at it, think about it, and figure it out. But what if you're not good at statistics? Or what if you're just someone on the floor who doesn't have an education in this? You need something simple. You need to know whether you're in control or not. That's why we need to plot our control chart. But you see we have our time values, our dimensional values, an upper control limit, a lower control limit, and an average. Now where did those control limits come from? Well, in Excel, you can easily calculate the standard deviation, also known as the sigma. Standard deviation is your average distance from the average. I'm going to do a separate video about that, but pretty much it helps you fit values to a bell curve. The rule of thumb with control charts is that you always want to be within 3 standard deviations above your average and 3 standard deviations below your average. This is also known as a 3 sigma spread, which means 99.7% of your parts will be good. That means only 3 in 1,000 parts will be bad. That's a pretty good production facility. So here is our data plotted on a control chart. You'll notice the line in the center that's moving up and down and changing values. That is your value data plotted over time. Then you've got the straight lines above and below it. Those are your upper and lower control limits. Then you have the line that fits pretty much in the center of all the moving points. That is your average. These were all taken from the table. This would be an in-control process. If you see a control chart that looks like this, you're producing good parts. Nothing is wrong so far. Let's look at some examples of out-of-control processes. If you have a point that's outside of one of your control limits, upper or lower, your process is probably out of control. This also most likely means that that point is non-conforming. It means the part is out of tolerance. If this makes it to the customer, you're going to have a quality issue. And I dealt with customer issues as a quality engineer for almost 2 years. It's a huge pain. Don't let these parts escape. Another sign that your process might be out of control is that you have 2 points that are both 2 sigma, which is standard deviations, away from the average in the same direction. Now, for my simple example, I only plotted 3 sigma away. But a more in-depth control chart would have lines at 1 sigma, 2 sigma, and 3 sigma. But my example is similar to how it would look. See how both of those points are very close to 3 sigma away? This could indicate your process is going to be out of control soon. This one can be a little harder to spot. If 4 out of 5 data points in a row are more than 1 standard deviation away from the average and in the same direction, your process could go out of control soon. So I circled some there, and what makes this one hard to notice is that you have the 1 point out of 5 that doesn't follow the rule. But see how the other 4 points are all above the average? If you have 8 data points in a row that are on the same side of the center line, which is your average, you might be going out of control. I've also heard this rule say just 7 in a row, so really it's up to you. But see how the ones I circled are all above the average? That's not good. That means you're running on the high side. It could mean you need to remachine your die, or for some reason you're processing slightly off. You have all that room below your average and above your lower control limit that you're not even utilizing. It's risky to be in this area because if you even go slightly higher, you're above your upper control limit. If you have multiple points in a row that are oscillating unusually, that is, you're constantly going above your average, below your average, above your average, below your average, and so on, this is a sign that you might be out of control. It's also a sign that if you're using 2 different machines, 2 different molds, 2 different dies, the tolerances on those could be completely different. You could have machine A that's producing above your average, and machine B that's producing below your average. If they're both within tolerance, maybe you don't want to adjust it, but this is something to pay attention to. If you have 2 different machines that are producing parts with different tolerances, this could pose a problem if you're the only one that knows it. If everyone else assumes the 2 machines pretty much produce at the same level, they could do changes that would affect the machines differently. Say, for example, you have management implement a preventative maintenance measure. They say, hey, we're going to put a special coating on these 2 machines. It will help the machines last longer, but the parts they produce will now be slightly higher with this dimension. Well, for your machine producing below average, great, raise the points a little bit, you're fine. But for the machine producing above your average, it could raise the points above your upper control limit. And no one would know that unless you had some sort of data that showed, hey, our 2 machines are producing at different levels. A control chart would be one way to catch this. Just like the example shown here. This might be 2 different machines working together. So all the examples I just showed are reasons why control charts are great. If I had just showed you the tables of numerical data, you probably wouldn't be able to spot the out of control points. And you probably wouldn't be able to notice trends, at least not right away. That is what is so great about control charts. But here are some extra notes. There are always a lot of scrap pieces when starting a production run, usually anyway, so keep this in mind when creating control charts. Don't start your chart the first 20 minutes of production. It's very common that your machines have to warm up, and in the process, create a few bad pieces. Also keep in mind that control charts are continuous tools. Don't use them for a week and then just say, hey, we're in control, I can stop using them. That's a horrible idea. Also, just because the points fit a rule doesn't mean you're out of control. You have to use a little bit of common sense combined with your run history to determine true control. Maybe your points oscillate for some reason, or maybe you do have a point that goes out of control occasionally. Doesn't mean your whole process is screwed. You have to take into account how you normally run and some other common sense items. You can also make notes on your control charts. This can be really useful. You can circle a whole area or just a few points and point out some items of interest in your production history. Thanks for watching this video. I hope you learned how to construct a control chart, why they're useful, and how to know if you're in control or out of control. You'll see these charts used a lot in industry, but you can use them in other areas besides manufacturing. Implementing these charts anywhere, and you're probably guaranteed to see some sort of improvement. At the very least, you can catch some mistakes, or prevent some from happening. So thanks for watching, and I hope you use control charts in your future. Good luck!